in this video, I'm going to be looking at some questions on enthalpy changes. So specifically, I'm going to be focusing on, ones that ask you to use the formula Q equals mc delta T. So this is a formula that you may well have come across back at GCSE level. It's one that is used a fair bit at A level as well and links to a number of topics in the second year. So I'm just going to go through a couple of questions where we need to use this formula to work out the enthalpy change of a reaction or combustion, for example, of different from different questions. There are different ways of asking this, so you can use spirit burners to heat up some water, which is what this first question is asking about, and you can also measure the temperature change of an exothermic chemical reaction, such as when you have an acid and alkali reacting. So we'll jump straight into it because these questions are always very much the same, and they are quite easy marks if you can remember how to do it. There are some common traps that students fall into, which I will also talk about. So without further ado, let's have a quick look then. So straightforward spirit burner apparatus, lots of writing. So the student is combusting, so let's just quickly highlight the key points here that you're going to use. So 1.54 grams of the alcohol, you've got 180 grams of water, and you're changing the temperature from 22.8 to 75.3. They give you the heat capacity in the question. It's also on your data sheet. And you need to calculate the amount in moles of alcohol J that burns and the enthalpy change of combustion. So they're not always that specific. They sometimes just say calculate the enthalpy change of combustion. So let's run through what we need to do then. So as I mentioned then, this is Q equals mc delta T. Okay, this is a very straightforward equation. So M is the mass of water. So from our equation, from up there, we've got 180 grams of water. Now, this is the thing: the density of water is 1 gram per centimeter cubed. So even if they'd written centimeters cubed, it wouldn't matter. It's still 180. Okay, so even if you get the numbers of centimeters cubed, it's still the same in grams. So just keep that in mind. Notice as well, the M in Q equals mc delta T is the mass of the liquid that is being heated, not the mass of the alcohol that is burning. Okay, the most common mistake one of the most common mistakes I see is students would be using 1.54 as M instead of 180. Okay, the 1.54 grams of the alcohol is what's burning. We need to work out how many moles of alcohol burn later on. Okay, we're not interested, okay, in anything else. Okay, the water is the part that you need to put in Q equals mc delta T. An easy way to remember it, the M in Q equals mc delta T is whatever you put your thermometer in. I'm putting the thermometer in the water, therefore I need to use 180. So let's quickly run this through then. So I need 180. I multiply by the heat capacity, which is C. They give you that. It's also on your data sheet, 4.18. And I'm multiplying it by delta T. Now, delta T is just the change in temperature, so 75.3 minus 22.8, and you get 52.5. Nice and straightforward. Now, another little mistake that students make here is, I'm sure you may have been told when you were taught this, that the delta T has to be in Kelvin. And what people tend to do here is take 52.5 and add 273. That is wrong, and you will lose marks immediately. Okay, you cannot do that. If you want to do this in Kelvin, you have to convert both of these numbers to Kelvin by adding 273 and then work out the difference. Spoiler alert, it's 52.5. So this is the thing with the Kelvin scale. Yes, it's 273 more than Celsius, but the difference is the same. If I increase the temperature of a room by 1 Celsius, I'm increasing it by 1 Kelvin. Okay, think of it like a staircase. 0 Kelvin is, 273 Celsius. No, it's not. My bad. 273 Kelvin is 0 Celsius. My bad. So, 0 Kelvin is minus 273 Celsius. They're just shifted in distance. Okay, think like a staircase. The Kelvin scale starts at 0. Celsius starts at, minus 273. But as you go up each step, it's the same amount. Okay, we're just going up by 1 every time. 1 Kelvin difference is the same as 1 Celsius difference. So you don't actually need to convert it. So please don't. When you get these numbers in the exam, never convert them to Kelvin. Leave them in Celsius, just work out the difference, plug it in and move on. You'll thank me later. All right, do this quick multiplication. Okay, it's nice and straightforward. Okay, and you end up with 39,501 joules. I'm going to convert it to kilojoules now because we need kilojoules on our answer line. So just divide by 1,000 and you get 39.501 kilojoules. It doesn't actually matter when you convert it. I tend to do it here just because it makes more sense to me to make sure I get it out the way. Now, you want to work out delta H. Delta H is Q divided by N, and N is the number of moles of fuel that was burned. So we know what Q is because Q is 39.501. We now need to work out N. Now, N is the amount of alcohol that was burned. So we need to do mass over molar mass. So we need to do 1.54 over the molar mass of alcohol J. Now, alcohol J, I'm told at the top of the page, so be careful, they've hidden this at the top deliberately, C5H12O. Okay, so that is 7, so that's 88 in terms of MR. So you're going to have 12 times 5, which is 60, add 12 is 72, add 16 is 88. So quick division, 1.54 over 88, and we get 0.0175. This now plugs directly in down here, so that's our N, 0.0175, and then we just do the division, so 39.501 divided by that gives me 2257.2, and there's my answer. Now, bit of exam technique again here. Make sure you read the question. It does tell you quite specifically to give your answer to 3 significant figures, so we need to round this a little bit. So the actual answer is going to be 2260. 3 significant figures. Remember, trailing zeros don't count as significant. And there is one final thing that students forget all the time. Okay, if you write 2260, you get 3 out of 4. Okay, you're working out a delta H. And the delta H is the enthalpy change of reaction. And we know the temperature is going up. Now, if the temperature goes up, it means it has an exothermic reaction. I'm going to underline that a million times. It's exothermic. If it's exothermic, delta H is negative. Now, you have to manually put that in yourself because there are no negative numbers in this calculation. But you must ensure that when the temperature is going up, delta H has to be negative. Okay, there is no negotiation to be had there. If you do that though, you get 4 marks. And if you get into the habit of doing these questions properly and well, you'll pick up marks no problem. So, calculated value is different. Apart from heat loss, which is the obvious one, suggest 2 reasons for the difference. Assume the calculation is correct, so we can't just say human error, but there's a load of reasons we can give here. There's actually loads of reasons. I'm just going to give you the 2 most obvious ones that you should be using. So we're working out the standard enthalpy of combustion effectively, or the enthalpy of combustion. Is it standard? Yeah, enthalpy of combustion by definition is under standard conditions. So the definition of enthalpy of combustion is when 1 mole of a fuel is burnt, completely in oxygen under standard conditions, and the energy change is calculated. So 2 reasons for the difference. First one, non-standard conditions. I don't know many laboratories that actually conform to standard conditions. So that's reason number 1. I don't think I've ever carried out carried out an experiment at 298 Kelvin, if I'm being honest. 25 degrees is hot for a lab, so don't think I've done that. And the second one is we are assuming it is undergoing complete combustion. It probably isn't. Okay, not all of it, most of it will be, but some of it will be in complete combustion, which is not the same. So we're going to have some incomplete combustion in there as well, which changes the outcome. So apart from heat loss, if you're ever asked to give reasons. I mean, obviously, if they don't say apart from heat loss, say heat loss, but apart from heat loss, and that's a terrible bit of underlining there. Apart from heat loss, non-standard conditions, and incomplete combustion. Right. I'm going to run through the second one very quickly because it's very similar. I'm not going to go through the whole Q equals MC delta T thing again. I'm just going to plug in the numbers for you because it's very straightforward. So they've added some magnesium to some silver nitrate, measured the temperature change. Now, we're still using Q equals MC delta T, okay? Only this time there isn't any water, but I will have put my thermometer in the reaction mixture. So I've put 25 centimeters cubed in a cup. That's where the thermometer is going. I've added a small spatula of magnesium. Now, it hasn't told me how much magnesium there is. So therefore, I can assume it doesn't matter. Now, in other questions, they might tell you how much there was. And if they tell you how much there was, it should be added on. Okay, so just keep an eye out for that. Okay, if they don't tell you the amount in the question, then you can't add it on. But if they do give you the amount, or they give you the masses of the two solutions and you can take them away, like they might have the mass of the solution at the beginning, mass of solution at the end. If you can take the difference from that, then do so and use that as M. In this case, we can't do that. So we have to do 25 multiplied by 4.18 because it tells us in the question that the heat capacity is the same as water, so nothing to worry about there. Delta T, again, I am not converting to Kelvin. 47.5 minus 19.5 is simply 28. Multiply all of that together and you get 2,926. And I'm going to just convert that, of course, into joules, 2.926. Sorry, kilojoule. I'm going to convert to kilojoules, 2.926 kilojoules. Now, we need to work out the number of moles. So this is important, okay? Now, we don't know how much magnesium there was, and it does say to us that all the silver nitrate has reacted. So we're just going to work out the moles of the silver nitrate because we're given a concentration and volume in the question. So moles of silver nitrate, N equals CV, and that's going to be, well, 0.512, which is the concentration, multiplied by 25 over 1,000. And if we do that, oops, we're going to get 0.0128. And then we just have to do Q over N. So Q over N equals 2.926 over 0.0128. See, it all gets repetitive, doesn't it, at this point? 2.926 over the answer. And we get 228.59, blah, blah, blah. Now, is that my answer? Not quite. Okay, I mean, first of all, you're probably saying to me, you forgot the negative sign. That I have. I have forgot the negative sign, but I've also forgot something else. Because this is one of those little tricks where you have to look back at the question and look at the number. So what you've just worked out is the number of kilojoules per mole, as in 1 mole. So this is kilojoules per single mole. The question, there's 2 of them. So if I had 1 mole of silver nitrate, the answer would be, well, minus 228.59, blah, blah, blah. I've got 2 moles of silver nitrate. Therefore, my answer has to be multiplied by 2. Okay, it's a really important thing that people miss out. Okay, if you've got more than 1 mole in your equation, the number you work out originally is for 1 mole. If there's 2 in the question, you've got to multiply by 2. Okay, so that means that your final answer is going to be minus 457. Okay, and I'm putting it to 3 significant figures because all of the numbers in the question are 3 significant figures. Okay, and it does say an appropriate number. So an appropriate number of significant figures is essentially you stick to the lowest number of significant figures that they use in the question at any point. So all the numbers here are 3 sig figs. So I give my answer to 3 sig figs as minus 457, and I get it correct. So there you go. Q equals MC delta T then is fairly straightforward. There are a few common traps that people fall into, such as not putting the negative sign, not paying attention to the number of moles in the equation. The mass of the liquid is very important. You have to use the mass of whatever you put the thermometer in, not the mass of the fuel being burned or something like that. And again, if I have 2 beakers and I'm adding 2 liquids together and I add 2 lots of 50, then the mass of liquid will be 100 because I'm putting them both in the same beaker and then putting the thermometer in. So if you can get the hang of these, you will pick up an absolute ton of marks in exams because they're always the same theme, they're always the same idea, just variations with slight little tricks and traps to try and trip you up. But in reality, if you learn the common ones and how to spot them, then they shouldn't give you too much trouble.